All right, so day 4 of DSA practice. For my technical interview, I really wanted to just get down the fundamentals to a T like it's the back of my hand. So I'm going to go through the sleep code like beginner crash course on arrays and strings, hashing, linked lists, stacks and queues, and binary search, and really just ingrain and really understand the fundamentals again of the arrays, the strings, but the deeper inner workings to the question so I can be able to understand it immediately when I see it intuitively. Instead of trying to say, damn, okay, what do I do with this string? Or, okay, it's an array problem, so what do I do next? But from just reading the question and understanding it. So I'm going to start sharing my screen, and then I'm going to start with arrays and strings and go from there. Mm, share screen. Hold on before I share my share. Yeah, make sure this is out of here. Hmm. All right. Arrays and strings, in terms of algorithm problems, arrays and strings are very similar. They both represent an ordered group of elements. Most algorithm problems will include either an array or a string as a part of the input. So it's important to be comfortable with the basic operations and to learn the most common patterns. Array can mean something different between languages. For example, Python primarily uses lists instead of arrays, which are extremely lenient. And this initialization is as easy as array equals an empty list. You don't need to worry about the type of data you store in the list or the size of the list. Other languages like C++ require you to specify the size and data type of the array during initialization, but also have support for lists like standard vector and C++. Technically, an array can't be resized, and a dynamic array or a list can be. So arrays can't be resized. A dynamic array or list can be. In context of algorithm problems, usually when people talk about arrays, they're referring to dynamic arrays. In this entire course, we'll be talking about dynamic arrays as lists, but we will just use the word array. Similarly, strings are implemented differently between languages. In Python and Java, they're immutable. In C++, they're immutable. It's important to know the details behind arrays and strings for the language you plan on using in the interviews. We don't have time to go through all the different implementations for each language, so please research it. Research it for your chosen language if you aren't already familiar. Mutable, a type of data that can be changed. Immutable, a type of data that can't be changed. If you want to change something immutable, you will need to recreate the entire thing. Why should we care about something mutable or immutable? If you have an immutable array equals string A, B, C, and immutable string equals S. Immutable string S represents A, B, C. But you want to instead represent A, B, D, you can easily do, but you cannot do as such. If you want this string, you need to create it entirely from scratch. With such a small string, it's not a big deal, but sometimes you're dealing with strings with 100,000 characters, so creating new versions just to modify one character is very expensive. All of n, where n is the size of the string. And actually, I want to go through big O first. That just reminded me, I want to go through big O first. Okay, so introduction to big O. If you already understand big O, you can skip this article. Before we talk about big O, it's important that we first understand exactly an algorithm is, especially what exactly an algorithm is, especially in the context of LeetCode. An algorithm can be seen as a recipe for a computer to follow. It's a set of instructions that a computer will follow step by step to solve a problem. Algorithms take an input and produce an output. The output will be the answer to a question regarding the input. For example, let's say we had a non-empty array of positive integers, nums, and you wanted to answer the question, what is the largest number in nums? To answer this question, you would write an algorithm that takes an array called nums as input and output the largest number in nums. Here's an example of such algorithm. Create a variable max num and initialize it to 0. Iterate over each element num in nums. If num is greater than max num, update max num equals num. Output will be max num. Here we have written down a set of instructions that we follow. We will solve the problem. We can now implement these instructions in code so that a computer can quickly solve the problem. There are some important requirements for algorithms in context of LeetCode. Algorithms should be deterministic. Given the same input, the algorithm should always produce the same output. Basically, there shouldn't be any randomness. Algorithm should be correct for any arbitrary valid input. In our example, we said that nums is a non-empty array of positive integers. There are in there are infinitely many of such arrays, and our algorithm works for all of them. Note that if nums had negative numbers, the input would be invalid since we state that integers are positive. In fact, our algorithm would actually break before initialize max num to 0. So if all of nums was negative, then we would incorrectly output 0. Big O. Big O notation used to describe the computational complexity of an algorithm. The computational complexity of an algorithm is split into two parts: time complexity and space complexity. The time complexity of an algorithm is the amount of time algorithm needs to run relative to input size. The time complexity of an algorithm is the amount of time the algorithm needs to run relative to input size. The space complexity of an algorithm is the amount of memory allocated by the algorithm when run relative to input size. The space complexity of the algorithm is the amount of memory allocated by the algorithm when run relative to the input size. Typically, people care about the time complexity more than the space complexity, but both are important to know. Time complexity as the input grow, time complexity as the input size grows. How much longer does the algorithm take to complete? Time complexity as input size grows. How much longer does the algorithm take to complete? Space complexity as the input size grows. How much more memory does the algorithm use? So time complexity deals with the amount of input we put into our algorithm, and so it says depending on if the input size grows, how much longer does it take for the algorithm to run, and depending on the size of our input, how much space does it take? How complexity works. Complexity is described by a function math formula, which should the arguments to this function be. The arguments are variables defined by the programmer, but they should represent values that change between different inputs. And these values should affect the algorithm. For example, the most common variable you'll see is n, which usually denotes the length of an input array or string. In the example above, we could say that n is equal to the lengths of nums. Here, the lengths of nums is the value that changes between inputs, and it directly affects the algorithm. The longer nums is the more elements we need to iterate through, and thus the longer our algorithm will take to complete. Note that changing the later n denote this value is arbitrary. There's no requirement that we use n. It's just that n is the commonly accepted standard. We wanted to use banana, we can use banana. Yeah. In the context of LeetCode, there are some common assumptions that we make. When dealing with integers, the larger the integer, the more time operations like addition, multiplication, or printing will take. While this is relative in theory, we typically ignore this fact because the difference is practically very small and treat all integers the same. If you are given an array of integers as an input, the only variable you should use is n to denote the length of the array. Technically, you could introduce another variable, let's just say k, which denotes the average value of the integers in the array. However, nobody does this. Excuse me. When written, the function is wrapped by capital O or big O, Here are some examples: complex big over n, big over n squared, big over 2n, 2 to the n, big O log n, big O n times m. You might be thinking, what is m? Remember, we define the variables as these are simply examples with no associated problem. M could denote any arbitrary variable. For example, we could have, yeah, these functions represent the complexity. For example, we could say the time complexity of algorithm is big O of n, or the space complexity of my algorithm is big O of n squared. Calculating complexity, roughly your function calculates the number of operations or amount of memory, depending on if you're analyzing time or space complexity, respectively. Your algorithm consumes relative to the input size. Using the example from the above, find the largest number of n's. We have a time complexity of O n. Using the example above, find the largest number of n's. We have a time complexity of O n. The algorithm involves iterating over each element in nums. So if we define n as the length of numbers in our algorithm, we use approximately n steps. If you pass an array with a length of 10, it performs approximately 10 steps. If you pass an array with 10 million steps, it performs 10 million steps. Time complexity is not meant to be exact repetition of number of operations. For example, we needed to initialize max num equals 0, and thus we could argue that our array, this is not the point of the time complexity. The point of time complexity is to describe how the number of operations changes as the input changes. The number of iterations we do depends on nums, but initializing maximum doesn't. Being able to analyze an algorithm and calculate time complexity is a crucial skill. Interviewers will almost always ask for the algorithm's complexity to check that you actually understand your algorithm. You didn't just memorize, just copy the code. Being able to analyze an algorithm also enables you to determine what parts of it can be improved. Rules. There are few rules when it comes to calculating complexity. First, we ignore constants. That means O of, what is that, 9,999,999 to the n equals big O 8n equals O n equals big O of n over 500. Why do we do this? Imagine you had two algorithms. Algorithm A uses approximately n operations, and algorithm B uses approximately 5n operations. When n equals 0 or n equals 100, algorithm A uses 100 operations and algorithm B uses 500 operations. What happens if we use double n? The algorithm uses 200 operations and algorithm B uses 1,000. As you can see, we double the value of n. Both algorithms require double the amount. If we were to 10x the value of n, then both algorithms require 10x more. Remember that the point of complexity is to analyze the algorithm, but we don't care about algorithm if it's five times slower than the algorithm. For both algorithms, as the input size increase, the number of operations required increases linearly. And that's what we care about. Thus, both algorithms of O of n. The second rule is that we consider complexity as variables tend to infinity. Um, when we have additions like subtraction between terms of the same variables, we ignore all terms except the most powerful one. For example, big O 2 to the n plus n squared minus 500n equals big O 2 to the n. Why? Because as n tends to infinity, 2 to the n becomes so large that the other two terms are effectively zero in comparison. Let's say that we had an algorithm that required n plus 500 operations, so it'll just be O of n. So it has a time complexity of O n. When n is small, let's just say n equals 5. The plus 500 term is very significant, but we don't care about that. We need to perform the analysis as if n tends toward infinity. In that scenario, the 500 is nothing. The best complexity possible the best complexity possible is O of 1, called constant time or constant space. It means that the algorithm always uses the same amount of resources regardless of the input. Note that constant time complexity doesn't necessarily mean the algorithm is fast. It just means that the it just means that its runtime is independent of the input size. When talking about complexity, there are normally three cases: best case, average case, and worst case scenario. And most algorithms, all three of these will be equal, but some algorithms will have them differ. If you have to choose only one to represent the algorithm, time or space complexity, never choose the best case. If you have to choose only one to represent algorithms, time or space complexity, in most algorithms, all three of these will be equal, but some algorithms will have them differ. If you have to choose only one to represent the algorithm's time or space complexity, never choose the best case scenario. It is most correct to use the worst case scenario, but you should be able to talk about the differences between the cases. Analyzing the time complexity. Let's look at some examples. Let's look at some example algorithms in pseudocode and talk about their time complexities. Given an array with length n, so we iterate through our array with a variable nums, and then we'll just print those elements. This algorithm has a time complexity of O n. In each loop iteration, we are performing a print, which costs O1. The loop iterates n times, which gives us the time complexity O1 times n equals O of n. So we have 1. So given array with length nums. So we say for array in nums, and then we say for I, then what? So it's two loops. I'm not exactly sure what this is doing, but it says I equals if I is less than 500,000, then we're gonna add I plus 1. I'm assuming, or add I twice. So it might be just I plus 1, and then we print nums. So this will be O of n times, or be big O of 1 times n times m. And so that would just be big O of n times m, or with this. So the algorithm has a time complexity of O n, and each loop iteration we perform a print. Costs O1. This loops 500 times, which means each outer loop costs. Okay. It'll just be O of n, even though the first two arguments actually have the same time. In reality, the second argument is slower than the first one. They said it's correct to say time complexity is O n, but it's important to be able to discuss the differences between practicality and theory. Okay. Given an array with length of n. Okay. So this because it's the same.
Do you want chicken? Yeah. And let's go get chicken.
For num in array, for num2 in array, so we're iterating through the array twice. So since we're iterating through the array twice, our algorithm has a time complexity of O n squared, and each inner for loop iteration we're performing multiplication and print, which costs O of 1, which both cost O of 1. The inner loop runs n times, which means each outer for a loop iteration costs O of n. The outer loop runs O of n times, which gives the time complexity of O of n times O of n, or O of n times n, which is O of n squared. So given arrays with length n and array 2 with length m, so for num and array, print for num array, so it would be O O2N, no, O, would this just be, so yeah, O2N plus M equals O, okay, that makes sense. These are the same because you're just going through the same array twice. So this would be O2N plus M. You're not multiplying. This algorithm has a time complexity of O and N plus M. And the first two for loops both cost O of N, correct? Whereas the final loop costs O of M. This gives the time complexity of O2N plus M, given an array integers array with length N. So we'll say for I and for I an array, if I is less than the length of array plus equal I, and then it says for and then it says, so really if j equals I, so we're going through the array again. We're going through the length of the array again, but looking for j, but now we're looking for j. And then once we found our I and our j in the array, we'll just add both of them and print it. So yeah, that makes sense because we're going through the array twice. This algorithm has a time complexity of O n squared. The inner for loop is dependent on what the iteration the outer loop is currently on. The first time with the inner loop is run, it runs n times. The second time, it runs n minus 1. Then n minus 2, n minus 3, and so on. That means the total iterations is 1 plus 2 plus 3 plus 4, which is the partial sum of the series, which is equal to n times n plus 1 over 2, which is n squared plus n over 2. And big O, this is of n squared because the addition term is the numerous constant term. So yeah, so we have for I and the length of arrays, if I is less than the length of the array plus equal I, and then we have j equals I. So if we have j equals I, well, it really doesn't even matter that we have j equals I. We're actually going through the length of the array again, but we're looking for j. And so if j is less than the length of the array, j plus equals, and then we're just going to add itself, and then we'll print the I and j in the array. And so because we're going through the array, or we're iterating through the array O of n times, or 2 times, it'll be O of n squared. The logarithmic time is the inverse operation to exponents. The time complexity O of log n is called logarithmic time, and it's extremely fast. A common time complexity is big O of n times log n, which is reasonably fast for most problems, and it's also the time complexity of efficient sorting algorithms. Typically, the base of the logarithmic will be 2. This means that if your input is size n, the algorithm will perform x operations where 2x equals n. However, the base of the algorithm doesn't actually determine for big O, since all algorithms are related by constant factor. O of log n means that somewhere in your algorithm, the input is being reduced by a percentage at each step. A good example of this is binary search, which is a searching algorithm that runs of big O log n time. There is a chapter dedicated to this binary search later on. With binary search, we initially consider the entire input n elements after the first step. We only consider n divided by 2 elements after the second step. We only consider n divided by 4 elements, and so on. At each step, we are reducing our search space by 50%, which gives us a logarithmic time complexity. Analyzing space complexity. When you initialize variables like arrays or strings, your algorithm is allocating memory. We never count the space used by the input. It's bad practice to modify an input, and you usually don't count the space used by the output unless the interview asks us to. In the below examples, the code is only allocating memory, so we can analyze the space complexity. So we will consider everything we allocate as part of the space complexity. Given an array uh, with length of n, the algorithm has a space complexity of big O of 1. The only space allocated is an integer value num, which is constant relative to n. So let me hide this. I don't want to look at the answer. Given an integer array with length of n, array double. So we have an array, and it's called double nums equals an empty list of integers, and then we'll say for integers, this will be O1, correct? No, this will be O of n stores, and at the end of this algorithm has a space complexity of O of n. The array double nums stores n integers at the end of the algorithm. Okay, double nums to add, and then we add it. So this is O1, but this adding this to make it O of n. So okay. So this algorithm has a special complexity of O of n. So we have an array called nums, which is just an empty list of integers. We have an integer which is called 100th, which is just equal to n divided by 100. And so I feel like this operation right here is O of 1. I feel like this is also O of 1 as well. But now we're adding our I. Now we're looping through our array to find our integer that is less than 100th, and then we're going to I feel like this is like a plus equal, and so we'll say nums to add, and because we're adding our iterated integer or n into our empty integer or empty list, it should be also like O of n. So the algorithm has a special complexity of O n. The array num stores the first 1% of numbers in array. This gives us a space complexity of O of n divided by 100. And if it was just 100, it just been O of 1, which was just been constant. So yeah, this is constant, and this is constant as well. But because we store it, this is O of n, and then given an integer array with length n and array 2 with length n, we have an array which is we call grid, which stores an integers, which is stores in the length of array 1 and array 2. And then we'll say for I and the length of the array. So right now this is O of n. This is O times m. And then the space, since we're only worried about the space, It's O1. No, it's O of n.
Mommy.
Creating a grid that has dimensions of. Okay, so we create a grid. What you doing? The algorithm has a space complexity of O n times m. Of course, so we have O. So O of n times m. We are creating a grid that has dimensions of O of n times m. Okay. Okay, let's go to, in this course we talk extensively. Practice should come. Okay, so I'll have to keep going back on that, but I think that was a good introduction piece to it. So now we start getting to more stuff. Where did I leave off? Mutable. So mutable, a type of data that can be changed. Immutable, a type of data that cannot be changed. Why should we care about something being immutable or not mutable? So I read this part. As, so yeah, but sometimes we're dealing with strings with 100,000 characters, so we're creating new versions just to modify one character. It's very expensive, which is OM. N, where N is the size of the string. As mentioned before, a majority of the algorithms when problems will involve an array or string. They are extremely versatile data structures, and it's possible to list all the relevant problem-solving techniques in one article. In the next few articles, we'll go over the most common techniques, but first, let's take a quick look at the complexity of array and string operations. Appending at the end, it's just O1 for arrays and list. Popping from the end is just O of 1. Insertion not from the end is O of n. Deletion O of n. Modifying an element O of 1. Random access O1. Checking if element exists O of n. String appending to the end of n. Popping from n of n. Insertion not from n of n or big O of n. Deletion from not from the n. And then random access, and then checking the elements. Appending to the end of a list is amortized. Oh, appending to the end of a list is amortized big O of 1. Okay, so yeah, let's go to the next one. 2 pointers. The format of this article is the format that many articles in this course will take. We will introduce ideas. 2 pointers is an extremely common technique used to solve array and string problems, and involves having two integer variables that both move along an interval. In this article, we will focus on arrays and strings. This means that we'll have two integers, usually named something like I and J, or left and right, which each represent an index of the array or string. There are several ways to implement 2 pointers. To start, let's look at the following method. Start the pointers at the end of the input, move them towards each other until they meet. Converting this idea into instructions, first start one pointer at the first index 0 and the other pointer at the last index input dot length -1. Use a while loop until the pointers are equal to each other. At each iteration of the loop, move the pointers towards each other. This means that either increment the pointer that started at the first index, or decrement the pointer that started at the last index, or both. Deciding which pointer to move depending on the problem we're just trying to solve. Here's a pseudocode. So we have a function. We define a function called fn, which just takes an array. We initialize our left and right pointer. So our left pointer equals 0, our right pointer equals the array. So the length of the array -1. So we say while left is less than right, and then we'll either add, it'll be left plus equals 1, or right. The string of the sentence is that we will never have more than The strength of this technique is that we will never have more than O of n iterations for the while loop because the pointers start in away from each other and move at least one step closer at each iteration. Therefore, we can keep the working side each iteration of O1. This technique will result in a linear runtime, which is usually the best possible runtime. Let's look at some examples. I'm closing my eyes because I'm trying not to look at the answer because I know the answer is coming up. I want to press Control A, remove that. Delete, 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 delete. Is that deleted? I was trying to look at it, but oh, they gave it to you. Damn. I think it's gonna be a problem that I could do at the end. Actually, what I'll do is curse. I could just. I'm doing the video. I'll do it like this. So I'll do terminal, and then I'll do cursor dot. Cursor dot. Um, where is my stuff at? I forgot the name of my project. Okay. DSA. Meet code. Gotta delete some stuff on my laptop. It's starting to run. I just ran cursor and this my laptop. I can hear my laptop right now, so yeah, definitely need to delete some stuff. But anyways, let me like this. Move that over. I forgot how you hide this. It's fine. Yeah, so strength. The strength of this technique is that we will never have more than O of n iterations for the while loop because the pointers start in a way from each of the other, and we move at least one step closer at each iteration. Therefore, if we keep the working side each iteration of O1, this technique will result in a linear runtime, which is usually the best possible runtime. Let's look at some examples. So we have the first example. So given a string s, return true if it is a palindrome, false otherwise. A string is a palindrome if it reads the same if it reads the same forward as backward. That means after reversing it, it is still the same. So class solution invalid colon taking itself taking the string. Are we taking s, which is just a string? And then we want to return a boolean, a bool. We want to return a bool, and then we say now the way I'm thinking that we can do this, if we have, for example, it says strings about genre if it reads the same. If it reads the same forward as backward, that means after reversing it, it is still the same string. So we can set a left pointer and right pointer. So we'll just say okay, left, right equals 0, and then the length of s minus 1. Then length of s minus 1. While left is, or I guess we could start off saying like this: if left to right, so actually now when you think about it, the left and right pointer have their integers should be equal to each other. So if left and right, so if left, so first if left is less than is so we say if left left not equal right, can we just return? We should just return false. False. We should just return false. If left does not equal right immediately, if left does not equal right immediately, then this shouldn't be. Then this shouldn't be a palindrome. So also we could say while left is less than right, okay, I'm just keep going. Could hear from more deep. Okay. After reversing a string, the first character becomes the last character. If a string is the same after being reversed, that means the first character is the same as the last character. The second character is the same as the second, and so on. We can use the second pointer technique or the 2 pointer technique here to check all the corners where the characters are equal to start. We check the first and last characters using two separate pointers. Yes, that makes sense. To check the next pair of characters, we just need to move our pointers towards each other or other one position. We just need to move our pointers towards each other one position. We continue until the pointers meet each other or we find a mismatch. We keep track of two indices, my left and right. In the beginning, the left index points to the first character and the right index points to the last character. If these characters are not equal to each other, we know the string. Yes, we know the string is not a palindrome, so we return false. Otherwise, the string may be a palindrome. We need to check the next pair. To move on to the next pair, we need we move the left index forward by 1, so plus equals 1, and then we'll minus our right index by 1. Again, we check if the pairs are equal. If they're not, and if they aren't, we return false. We continue this process until we either find a mismatch, in which case the string cannot be a palindrome, so we return false, or the pointers meet each other, which indicates we have gone through the entire string, checking all pairs. If we get through all pairs without a mismatch, we know the string is palindrome, so we can return true. To run the algorithm until the pointers meet each other, we can use a while loop. Each iteration in the while loop checks one pair. If the check, so say while, would it be like that? Okay. To run the algorithm, iteration, if check is successful, we commit left, decommit left, and decommit right to move the next pair. The check is unsuccessful, return false. All right. And so let's say while. Okay, so while left, yeah, while left, right. So if s. So right now these are just pointers. So these are just pointers. Let's actually think about this. So these are just pointers. We just initialize pointers. These pointers have not been added to our string to be properly placed. And so in order to place them, we need to first loop through our while our string, and say first we need to do a while loop so we can increment our left and right indexes. And so to add our left and right indexes to the appropriate places, and we can just say s of less and s of right. But we want to check, or we know that if the first element does not equal the last element in the string, then it can't be a palindrome. So in order for us to have our pointers at the correct index of the string, we just say if s of less of left is not equal to s of right, we return false, and then it'll be left or L plus equals 1, right? Plus equals, all right, equals 1, and then return true. Okay, so let's go through this again. So we have I'm just gonna write this out too. So ex1, actually I could do it like this. Tripping. Example, I'm tripping. Let me just do this. Boom. And I want to be able to see it more for right now. Okay. Given a string S, return true if it is a palindrome, false otherwise. A string is a palindrome if it reads the same forward as backwards. That means after reversing it, it is still the same string. For example, A B C D C B A B C D C B A R A C E C A R R A C E C A R. So yeah. So from the front to the back and from the right to the left, they're the same. And this in this example or this question, we definitely use a two-pointer approach. A two-pointer approach because it allows us to check to see if the elements or the characters in our string are equal to each other, and if they're not, then we obviously know it's not a valid palindrome. And so we can start the first. Let's just say class solution, and just create a function called valid palin, which will just take in itself. We'll take an s, which s is just a string, and then we just want to return a boolean value. And so first we need to initialize our left and right pointer. So we'll just say 0 and then the length of s minus 1. And we want to, now we want to do a while loop through our left and right index. And so we'll say while left is less than right. And so we understand in order to find a valid palindrome, if the left and right index or characters aren't equal to each other, then we should return false. And so we immediately stop the algorithm because we know it's not a valid palindrome. So we can write that as if s of left is not equal s of right, we can just do left or L plus equals 1, and then R minus equals 1, and then we will just return true. Notice that if the input was an array of characters instead of string, the algorithm wouldn't change. The two-pointer technique works as long as the index variables are moving along some abstract iterable. This algorithm is very efficient as not only does it run off in O of n, but it also uses O of one space. No matter how big the input is, we always use two variables. Excuse me. The time complexity is O of n because the while loop iteration costs O of 1 each, and there can never be more than O of n iterations of the while loop. So we have a while loop. Yep, that makes sense. So we just O of n, everything else is constant space. And everyone O of n, the pointers start at a distance of n from each other and move closer by one step each iteration. Okay. We have example 2. Okay. So it's a class solution. So example 2, given a sorted array of unique integers and a target integer, return true if there exists a pair of numbers that sum to target, false otherwise. The problem is similar to two-sum. In two-sum, the input is not sorted. So we have a sorted array, we have a target, and we need to return a Boolean value true if our elements in nums equals to 13. So we just need this. If there's a pair within a given array that returns 14 or 13. So we'll say define a function called sort R, which is taking itself. We will have nums, which nums is just a list of integers, and then we'll have our target, which just is an integer, and then we want to return a bool. And so given a sorted array, that would have been tragic. Given a sorted array of integers and a target integer, return true if there exists a pair of integers that sum. So okay, let's start off. So left, right equals 0. We want to initialize our pointer 0, and then the length of nums minus 1. And now we want to add our pointers to our. We want to add our pointer, or we want to iterate through dubs. So we say, well, if you're right. If this is nums of okay, well, if it's less than right. Now what so so if so okay, let me think about this. So we're giving an array of nums. We have a target. We want to find out where the target is. The way we find out what our target is we are adding the two elements in our array. And so we just initialize our left and right pointer in our sorted array, which will start at first index, which is 1, and then the last index, which is 15 in this example. And so we need to sum these two numbers. We need to sum these two numbers. And so if so if so okay, we can do it like this. So if nums are left plus nums of right equals target, if nums L plus nums right equals target, return true. Return true. And so if plus nums are right equals target, we return true, else Else we can just say L. Can we just do the same thing? Minus. This is wrong. But my thought process right now is if left and right equals target, then we will just immediately return true. Right. Else, then our left pointer we'll move our left pointer to the right, and then we'll decrement our left pointer to our right pointer to the left until we find a sum that equals our target. So that's where I'm thinking. But let's look at the brute force solution would be to iterate over all pairs of integers. Each number of array can be paired with another. So this would result in a time complexity of O of n squared, where n is the length of the array. Because the array is sorted, we can use 2 points to improve to O of n time complexity. On O of one space complexity, use an example with 2 pointers. We start by looking at the first and last numbers. Their sum is 1 plus 15, which is 16, because 16 is greater than the target. We need to make our current sum smaller, therefore we should move the right pointer. Now we have it again. The right pointer becomes too small. Since it's small, we need to make it bigger. We move it again. The reason this algorithm works because the numbers are sorted. Moving the left pointer permanently increases the value. The left pointer points to num to left equals x. Similarly, moving the right pointer permanently decreases the value num to right. If we have x plus y is greater than target, then we can never have a solution with yx because so if a solution exists, we can only find it by decreasing y. The same logic can apply to x if x Okay, that makes so much sense. Okay. So I wasn't damn sure wasn't too far off from where I was. So that's actually amazing. And anyone's watching this shit, we're coming a long way. Like, really thank the people I was talking to just yesterday that really kept me motivated. Because I, looking now and understanding, I should have said, actually, let's not look at it, but let's just keep reading the solution. And now we've seen it once. Like I said, if I see something once, I kind of like get an understanding. But I want to make sure that they're just putting check and then they're just doing it like that. So that's fine. Okay, so let's again initialize our left and right pointer. Given a sort of array of unique integers and a target integer, return true if there exists a pair of numbers that sum to target, false otherwise. This problem is similar to two sum and two sum. Okay, so if our left and right pointer equal to the target, then we'll return true. Otherwise, we'll return false. And so right now, what I'll do is just initialize our left and right pointer. So immediately when I see this question, I know that we're going to use a two-pointer approach where we're going to initialize our left and right pointer at the first and last index of the list. And then we'll try to add our left and right indexes or elements at the left and right, or the elements at those specific pointers or whatever time to find our target. And so we to initialize our left and right pointer, we'll just say left equals 0, and then right equals the length of nums minus 1. And to iterate through or to increment and decrement through the array, we need to have a while loop. So we'll just say while left is less than right. So because left is less than right, in this example, let's think about this. In this example, we know if our left and right pointer, if we sum our left and right pointer or elements at the left and right pointers and they equal our target, then we should return true. So we can create a variable called current to track the addition of each of those elements, and if again if our current is equal our target, then we should just return true. So we'll make our current equal to nums left plus nums uh, nums right, and then we'll say if current equals if current return true, return true. And then I feel like, let me look at it. Then it's another if statement, and then it's if. Okay. I'm hearing my baby torture her great grandma. So that distracted me for a second. But if the current is greater than the target, then we're going to know we're going to decrement our right pointer -1. So if current, and then we'll just say right equal or minus equal 1, and then else left plus equal 1, and then we'll return false. Okay. And again, that makes sense. It's starting to make sense. We initialize the pointers. In order for us to iterate through our pointers, we need to say while. We need to set a while loop, and then we need to uh, essentially add our pointers into the array or the string. And so we'll just say nums of that. We'll just say nums of left and right, and then for our current or for our actual question, we had to sum our elements in our array nums to find the target, which was 13. So we set our pointer to the first element and the last element, and the first element, which is 1, the last element, which is 15. When you add those, you get 16, and because 16 is greater than 13, it doesn't make sense to add the left pointer. It makes more sense to subtract the right pointer, and unless we subtract the right pointer and gets to a place where that is big or is smaller than the target, and then we have to add our left pointer. But we just need to subtract our right pointer until we get to our target. If else, then we'll increment our left pointer to the right. So okay, I'm just gonna write down one more time. We have our left pointer, we have our right pointer. So we initialize it, and then we set the length of nums -1, and then yeah, length of nums -1, and then we want to say while left is less than right, which it is. Our curve equals nums of left plus nums of right if curve equals target, return true if curve is greater than target, return target, which is in the beginning. Then we just set our is equal 1 else f plus 1 return false. Makes sense. Okay, so another way to use two pointers. This method where we start the pointers at the first and last indices and move them towards each other is only one way to implement two pointers. Algorithms are beautiful because of how abstract they are. Two pointers is just an idea. Where are we? Just an idea, and it can be implemented in different ways. Let's look at another method and some new examples. The following method is applicable when the problem has two iterables and the input, for example, two arrays. Move along both inputs simultaneously until all elements have been checked. Converting this idea into instructions, create two pointers, one for each iterable. Hold on. Create two pointers, one for each iterable. Each point should start at the first index. Use a while loop until one of the pointers reaches the end of its iterable. At each iteration of the loop, move pointers forward. This means incrementing either one of the pointers or both of the pointers. Deciding which pointer to move will depend on the problem we're trying to solve. Because our while loop will stop when one of the pointers reaches the end, the other pointer will not be at the end of its respective iterable when the loop finishes. Sometimes we need to iterate through all elements. If this is the case, we'll need to write extra code here to make sure both iterables are exhausted. Here's some pseudocode. We have a function that takes in two arrays. And we want to set pointers for both of the arrays. So we set I and j equal to 0 for the first pointer, and say while I is less than the length of array 1 and j is less than the length of array 2. And then we're going to either add both. Step 4, make sure both iterables are exhausted. So while I is less than that makes sense. Similar to the first method, when we looked at this method, will have a linear time complexity of O n plus m. That makes sense. Because of this and. If the work inside the while loop is O of 1, where n is length and m, this is because of we move at least one pointer forward. The pointers cannot move more than n plus m times without the arrays being exhausted. Let's look at some examples. Let's try this actually. So given two sorted integers, arrays 1 and arrays 2, return a new array that combines both of them and is also sorted. First thing I think is if we have array 1 and array 2 and they have similar integers, for duplicates, doesn't matter if we have duplicates or we shouldn't have duplicates. Okay. And for this, I'm definitely thinking about using a two-pointer approach where we'll initialize the index at the first position for both. And we just say, first is define a function. Define a function. And we'll name this function. We'll define this function called 2int, which is just taking itself. We'll take in array 1, which is a list of integers. And then we have array 2, which is just a list of integers. And then we want to return a list of integers. And so we'll say I equals j equals 0, and while I is less than the length of array 1 and j is less than the length of array 2, returning the given two sorted integer arrays, array 1 and array 2, return a new array that combines both of them. So I'm going to have to concat both. So I'm going to have to add both and into a new. So literally, it's going to be something like return array 1 plus or it could be a variable which is new array. We have new array which equals array 1 I plus array 2j, and then we're going to return new array, or it could be something like array 2. But anyways, first we initialize our pointers. So we're starting the first index and last index, and so we're starting the first index for both, and we want to iterate through return a new array that combines both of them and is sorted. If so we're going to add we're going to add both. I plus equals 1, and then j plus 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 1. And then be another while I just in the length of array 1. Mm, mm. I'm just assuming. So while, and then while, then be the next while I is less than the length of array 2. Would this just be j, or then I minus equal 1, else j plus equal 1. I'm not sure. This might be dead wrong. And then return. Let's see. The trivial approach would be the first to combine both input arrays and then perform a sort if we have n equals array. N equals array 1. This gives the type complexity of n log n cost of sorting. This would be a good approach if the input arrays were not sorted, but because they are sorted, we can take advantage of the two-pointer approach to improve to O of n. In the previous example, we declared here we are saying n equals array 1, the length of array 1 plus the length of array 2. Why haven't we changed the definition? Remember that when it comes to big O, we're allowed to define variables as we see fit. We could certainly stick to using m and n. In that case, the array complexity of sorting approach would be big O of n plus m log and the time complexity times the time complexity of the approach would curve be about. It'll make no difference either way, but one justification would give us here is since we are combining the arrays, the total length is a significant number, so it makes sense to represent it as n, keeping the definition of n equals the length of array 1 and m equals the length of array 2 is fine. We can build that answer array one at a time. Each iteration you have two values. So we have an empty array. So will we have an empty array? Yeah. So we have to set an empty array. If array okay, we can build the answer array answer one element at a time. To start 2 points at the first index of each array and compare their elements. At each iteration, we have two values. Whichever value is lower needs to come first in the answer. So add it to the answer and move respective pointers. That makes sense. Sorting an array of length n costs O of n times log n. We can improve the time complexity by a factor of log n by taking advantage of the input array already being sorted. If we start the smallest number from each array, then whichever one is smaller must be before the other one. So we add it to the answer and move the next number to the array. If the values are equal, it doesn't matter which one we choose. We can arbitrarily choose either. This process can be repeated until one of the arrays run out of numbers. When this happens, we are still left with some numbers in the other array. These numbers are all larger than the largest numbers in the exhausted array, and we get this append to the answer. That makes so much sense. Okay, that makes sense. And I'm gonna read it again so we can just solidify that shit. So, sorting array will call so O of n times log n, but we can improve this time complexity of O of n by using a two-pointer approach. So if we start with the smallest number from each array, which is the first index, then whichever one is smaller, whichever one is smaller must be before the other. So we add it to the answer and move to the next number in the array. If the values are equal, it doesn't matter which one we choose. We can arbitrarily choose either. This process can be repeated until one of the arrays run out of numbers. When this happens, we still have left numbers in another array. These numbers are all larger than the largest numbers in the exhausted array. So we just add or append them to the answer. Okay. And so keep everything. We will have, actually, just do it like this. So we need to set an empty list called answer, which is going to that we're going to append or concatenate it or append our values to. We're going to have an empty list that we're going to append our values to at the end, and this is also going to keep track of the elements that we want in our list. And so we need to initialize our pointers and for each of the arrays. And so we just say for I equals j equals 0. And then we'll set a while loop. So we'll say while I is less than the length of array 1 and j is less than the length of array 2. So we're saying if the elements or if the elements in array 1 are less than the elements in array 2, we're going to append the elements in array 1, and then we're going to plus equal I. So that means we're just, once we append that element, we'll just move, then we'll move to the next element in the list. Else we'll append the elements in array 2, and then we'll move that iterator. And then it says while I is less than the length of array, while I is less than the length of array, which it should be. Okay, my laptop is about to die, but that's fine. We'll just go outside. You know what I'm finna do? I'm just finna put it in the room. Tell her go to sleep. Literally, y'all can do that now. Just tell her go in the room. It's night time. Go in the room. Rosie, come here, baby. Rose, come here, baby. So initialize empty list. You ready for night? No. Yes. You said you want what? It's night time, baby. Go in the room, okay? Go in the room and lay down. Go in the room and lay down. You want me to put on TV? Go in the room. You want me to put on TV? Go in the room and lay down. It's night time. Go in the room and lay down. It's night. It's night. Go lay down. Okay? Go, baby. So given two sorted integers, array 1 and array 2, return a new array that combines both of them and is also sorted. So we just return the answer. And so we set an empty list, or create an empty list that will store our answers and store and track our answers. And first we want to initialize our pointers. We just say I equals j equals 0. Now we want to initialize, now we want to loop through. Now in order to loop through our using our pointers, we need to say while I is less than the length of array 1 and j is less than the length of array 2. Array 1 I is less than, no, if is less than array 2. So if I is less than array 2, and then we're just going to do array 1 dot append. Then we're going to append array 1 I. Yep. And then I plus equals 1, else array 2 dot append array 2 j. And then we say while and the whiles will all be up here. Okay. So while I is less than the length of array 1, you just do I plus equals 1. And then while j is less than the length of array 2, j plus equals 1, return answer. Okay. So given two solution, and so because our arrays are sorted, this will make it easier. And so instead of having time complexity of big O of n log n, we can just have a time complexity of O n by using a 2-pointer approach. And so def 2-point self, we're just gonna have array 1, array 2, and then we're going to say answer equals an empty list. We'll set our pointers I equals j, and to increment and decrement our pointers through our arrays, we need to say, well, if array I is less than array 2j, then we need to do array array 1 I, and then else append j, while I is less than the length of array, and then we have 4, and then this would be j plus equals 1, because we're both starting the same spot, we're not going at least, and then we'll do I plus equals 1. All right, my laptop is about to die. Mic on a little bit later. Or what's my laptop charges?